define what polymers are. Then we're going to relate polymers to things that you interact with on a day-to-day life. If you are interested in polymers, there is a chapter of the textbook, chapter 27, that goes into it. There's also a brand new course, CHEM 4222, which is starting next year, spring 2026. I believe Professor Reineke is going to be teaching it, I think. And it's called Polymers for the People on the Planet. So this is redesigned with undergraduates in mind to sort of introduce you to the concepts of polymers and how they relate to everyday life. And then also some sustainability, green chemistry type things in there as well. So we're really excited about that new class. So if you are interested in polymers, please check it out. All right, so let's talk about polymers. So what is a polymer? I like to break it down. First, what does polymer mean? So poly means many, and mer means parts or like a specific like chunk of things. So that means that a polymer is therefore a long chain molecule consisting of many parts. And those parts, what a polymer is made out of, are called monomers. So mono means one, right? So you take a monomer, which is one part, and you put a lot of those together and you get a polymer. So they are long chain molecules that are consistent of many parts. But what does long mean? Like a long chain molecule, what does that mean? So to illustrate this, I like to just use hydrocarbons as an example, right? So we've definitely heard of methane before, right? Hopefully in both Gen Chem and maybe organic chemistry as well. So methane is a single carbon and 4 hydrogens, right? Methane is natural gas. So this is a gas at room temperature. The boiling point of methane in degrees C is negative 162. Okay, so that's why it's a gas at room temperature, right? So this is natural gas. We use it for gas stoves and things like that, right? So remember that boiling point is related to the molar mass of your molecule. So going from methane to octane, so going from 1 carbon to 8 carbons, right? So 8 carbon hydrocarbon. Octane is the major component of gasoline. So that means that it is a liquid at room temperature. And its boiling point is 125. Okay, so that's just by making the chain longer, increasing the mass of the molecule. When we go to icosane, so that's 20 carbons long. This is now a brittle solid with a boiling point of 343. And then you just keep making it longer and longer and longer. Eventually, you get to something called high density polyethylene, or HDPE. So this is just a linear long chain of CH2, 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 CH2 over and over and over again. So like, for example, if we have 10,000 carbons in a row, that's going to be high density polyethylene. And instead of being a brittle solid that breaks really easily, this is now a tough plastic. So this would be considered a polymer. And really, there isn't really a boiling point for these types of very long chain molecules, because before it boils, it's going to decompose or like burn, right? And so you can't boil them. They're too large. And so that's just an example of just using hydrocarbons. Of course, there are lots of different examples as well. But there's not just like, oh, once you hit this molecular weight, now it's a polymer. That's not really how it works, unfortunately. So it kind of depends on the properties. So we're looking for, when does it start acting like a polymer or acting like a plastic, that we sort of have that cutoff. So that's just as an example, but unfortunately it's not cut and dry. Okay, so now we know what a polymer is. How do we write a polymer? So like, why did I have this bracket here? So how do we depict polymers? So we usually have some like parentheses with something in the middle, like this, maybe with a subscript there. So what is in between the brackets is known as the repeat unit. So this is our repeat unit, or RPU, or just RU, but repeat unit. So it's the thing that repeats, right? So you just repeat whatever's in the brackets over and over and over and over again to make that long chain molecule. The bond here that goes through the bracket is a covalent bond, usually, that connects each of those repeat units. Okay, so essentially, this bond will connect to this bond of the next repeat unit. So I'll draw an example of that in a second. And then finally, we have this little subscript here. And this tells you the average number of times that the repeat unit repeats. And it's average because polymers have a distribution. So it's not exactly that many times, it's approximately that many times. And it's not always n. So this is a kind of an annoying thing about polymers, is that the nomenclature is not always consistent. So sometimes you'll see that n as x or I, or it'll be left off entirely. So you don't need the subscript there, but you're technically supposed to, but you'll see it a lot without. Okay, so let me give an actual example with actual structures. So you might be familiar with these types of cups, right? Styrofoam cups. So styrofoam is made out of a polymer called polystyrene. Right, so the styro in styrofoam comes from styrene. So polystyrene looks like this. Okay, so again, I have that bracket to show the repeat unit. And so I'm going to show what that actually looks like. So this continues on. So I'm not going to draw the entire polymer, obviously, because that would be too long. But I can draw my repeat unit. And then I'll change colors and I'll draw my repeat unit in a different color. And then I'll change colors and I'll draw it in a different color. And then I'll change colors and I'll draw it in a different color. So each one of these colors is representing another repeat unit, and that will continue on in both directions. Okay, so hopefully you can see that this is one repeat unit, and then it repeats again, and then it repeats again, and then it repeats again, etc., etc., etc. Right? So it keeps going in both directions. So each one of those is a repeat unit. And this is called polystyrene because it comes from a monomer called styrene, which looks like this. So this is styrene. Okay. So you can see that there are some structural similarities between this and our repeat unit. The difference is that this alkene, right, or olefin, the double bond in the monomer, is not in the polymer, because that was the part that we reacted. So here we have our alkene, aka olefin, in our monomer. That group can also be called a vinyl group, which essentially means like a terminal, terminal alkene. And so these polymers are often called vinyl polymers because it means that we reacted a vinyl group. We reacted that terminal alkene group. So that's one major type of polymers where you have an alkene in your monomer, and then you polymerize it so that you have basically the same repeat unit, just without that alkene. Another major type of polymer that we've actually kind of talked about a little bit earlier in this class uses chemistry that we're more familiar with. So an example of that would be nylon, right? So I'm going to show nylon 6. There's actually different types of nylon, but I'm going to show nylon 6 because that relates to what we've talked about before. 1, 2, 3, 4, 5, 6. So nylon 6 looks like this. So the 6 refers to the number of carbons in our repeat unit. So 1, 2, 3, 4, 5, 6 carbons in our repeat unit. And the broader structure of this, if I draw a couple of repeat units in a row, 1, 2, 3, 4, 5, 6. I'll change colors and draw another repeat unit. 1, 2, 3, 4, 5, 6. And I'll change colors and I'll draw another repeat unit. 1, 2, 3, 4, 5, 6. Okay, so again, we have these different repeat units, right, that are drawn in different colors. So hopefully you can see why we don't like to keep drawing it out, right? It gets really long, it gets really big and kind of unwieldy to draw. So that's why it's much, much easier to draw one repeat unit and then just put brackets around it, right? Because it's just a little bit easier to deal with. So the thing that we've talked about this before is that I mentioned it when we learned about lactams. So the monomer for this particular polymer is epsilon caprolactam, right? Remember, a lactam is a cyclic amide, and we open the ring to form this repeat unit. And so if you notice, right here, right, we have amide linkages in the backbone of this polymer, right? So that is a functional group that we've learned about in this class, right? Carboxylic acid derivatives. It's going to be an amide. So this type of polymer is called a polyamide because we have amide linkages, right? So that's similar with polyester, polyamides, things like that. Does that make sense? How polymers are written with the brackets? How it continues? Yeah? Okay. Okay, so that's kind of like how like major parts. There's some confusion with how things are named in polymers because this is a polyamide because there's an amide in the repeat unit. This is called a vinyl polymer because there's a vinyl unit in the monomer. So it is a little bit confusing. I don't know. It just kind of is what it is. But these are kind of our two major classes of polymers. So now you know what a polymer is. Now I want to see how much you know about what polymers do. So we're going to do our timing question before we keep going, just to see how much you are already familiar with polymers. So this is actually an open-ended question. So like things that we use in our daily lives that are made from polymers. You probably know some, and there's probably some that would surprise you. So let's see what you already know about. Here we got. All right. Plastics, yes. So plastics is a very broad term. So there's lots of subcategories there. Rubber, that's a really good one. Actually, a lot of rubber is a naturally occurring polymer, but we also can make synthetic rubbers. Tires, pipes, yep. Pipes can be a couple of different things. Clothing, yes, we're going to talk about that in a second. Cellulose is also a natural polymer. What else? Packaging, yes, there's lots of packaging that is made out of plastics. We're going to talk about that too. Paint, yes. Coatings, all of those are polymers. Containers, infrastructure, yep. Fabric, what else we got? Tape, yeah. So adhesives, those are also polymers. What am I not seeing here? Yeah, cooking things, styrofoam, string. I'm not seeing things like the seat cushions that you're sitting on. Those are polymers. What else? Floss, that's a polymer. There's lots of different things that are polymers. So yeah, that's good. I think that nowadays people are a little bit more informed about some things that are made out of polymers, right? Like water bottles and things like that. But there's actually a lot more than you see. I was good to see that like things like paint are known, like coatings, like those are all polymers as well. And so polymers are ubiquitous in our daily lives. They're used a lot for a lot of different things. Sometimes for the better and sometimes not so much for the better. But yeah, let's talk about a couple of them that I think are particularly interesting. So the plastic bottle, right? So this is a Powerade bottle, and polyester fabric are actually the same polymer, which I find kind of crazy. And so both of these are a polymer known as polyethylene terephthalate, which is like the weirdest word to spell. It's terephthalate, so PHTHALATE. It's a very obnoxious word, but polyethylene terephthalate, more often you'll see this labeled as PET or PETE. Okay, so if you ever see like a water bottle with PET on it, that this is this polymer. So let me draw the repeat unit of this for you. Okay, so that is our repeat unit. It's a pretty big repeat unit, like this guy, right? So if we were to continue on both sides, right, we would have another one of these continue. And then on this other side, we would have this part of the repeat unit continue. So just as a reminder of how that works. Okay, so just grow in both directions there. Okay, so why is this called polyester? Well, we have these ester linkages, right, in the backbone of the polymer, right? So these are esters. So it's called polyester because it is a polyester, but this is not the only polyester, but it is the polyester that's used for the fabric known as polyester. Okay, so this is a really common polymer. This is probably the polymer that is recycled the most, which is good, but it's still not recycled as much as it should be. But one of the cool things, and the reason I want to talk about it, is to talk about how it's made. So how do we make this? And because it uses chemistry that we learned in this class. So we use nucleophilic acyl substitution, which was all of chapter 20, right? So our carboxylic acid derivative reaction, right? Basically all of carboxylic acid derivatives undergo nucleophilic acyl substitution. This also does that. Yeah. Yeah. Thank you. So we're using nucleophilic acyl substitution. So let's look at the monomers for this polymerization. So, oops. We are going to have a carboxylic acid derivative. So again, this X group can be a couple of things. So we could have it be a chlorine. So we have a diacid chloride, right? Or we could have something like an OMe to have a diester. Okay. And then that would be our electrophile. So now we need a nucleophile. And in this case, it's going to be a diol. Okay. So we essentially have our electrophile, we have our nucleophile, right? But we just have 2 of them in each molecule. Okay, so it's the same functional groups that we've talked about previously, we just have 2 of them. And so the diacid chloride or the diester, right, having 2 of the same functional groups, we often call this like an A monomer, because we have 2 A functional groups. We label these as A. And then our diol is a different functional group, B, but there are 2 of them. So this would be a B monomer. And then you just react them together. So if we react these together, we lose HX using nucleophilic acyl substitution. Something like this. Okay, so I have made 1 ester linkage there. I still have 1 A functional group. I still have 1 B functional group. So that means that it can continue to react. And so, you know, 2 of these might come together, and then you have 4 kind of units long, and then those come together, and you'll always have 1 A and 1 B on the ends. So you just keep reacting to make that chain longer and longer and longer. And eventually you start getting those really cool polymer properties after that. So again, the reactions that we learned in this class, I promise, are actually used in real life. So this is how all of that polyester is made, even in industry. So that's cool. That's polyethylene terephthalate, or PET. Very, very common polymer that we use every day, but not as common as this next one. So plastic that you can like squeeze, right? So like lotion bottles that are like have some give into them, or things like plastic bags, often are actually made from the same material. So this is that high density polyethylene that I mentioned earlier. Which is abbreviated as HDPE, high density polyethylene, which is just this kind of linear CH2, 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 CH2 over and over and over again. So this comes from ethylene, which looks like this. Okay. And so a hint about the properties of this polymer, if you look at this bottle, right? This bottle is opaque, right? We can't see through it. And so oftentimes when you have a material that is opaque, that indicates that it is crystalline. So what does that mean? That means that the chains line up. Again, that continues on. Like so. And actually, sometimes the same polymer will come back around and line up with itself again, like this. Okay. And as those chains start to line up, you start getting those intermolecular forces in between the chains. So in this case, it's just London dispersion forces because it's just CH2s. But if you have a large enough molecule and you have so many of those forces, they will start to crystallize. So our chains line up and crystallize. Which gives different material properties. And oftentimes crystallinity gives better material properties. So it will have like better like strength, for example. But this is one of the cool things about polymers, is that you can actually access a really, really wide range of properties just by tuning things like crystallinity. So I like to use this example because this plastic bag and this lotion bottle, right, are the same material, but clearly they are quite different, right? These are very different objects. And so that tells us that it's not just what the polymer is made out of, it's also how do you process that polymer. And so that this is telling us that processing matters a lot. So that's a little bit more of an engineering topic as opposed to a chemistry topic. But if you're doing polymer chemistry, they're kind of interconnected because you can't really get away from both of them. But I like to use this example just because it's so ubiquitous. HDPE is one of the most used polymers for all of the things. Like a lot of the pipes that were mentioned before were also made out of HDPE, again, because they have really good properties. So what does this high density polyethylene mean, right? So most of the time we've been talking about you have a monomer, you get a polymer. You have a monomer, you get a polymer. So why do we need to specify high density polyethylene? Why can't we just say polyethylene? So that is because there are lots of different types of polyethylene, which are different isomers of each other. So in this class, right, we've talked about isomers before on the small molecule level. So for example, if you have just like a linear 4-carbon chain versus a branched 4-carbon molecule, right, those are isomers of each other. They have the same composition, right, the same number of carbons, the same number of hydrogens. They're just connected differently. So we can do that in polymers too, except a lot more because there's just so many more atoms. So there's so many more options that we can do. So HDPE is what we've been talking about, which is just linear, right? So it's just like this. So this is linear. And as we mentioned, it's highly crystalline. But that's not the only one. We can also have low density polyethylene, or LDPE, which is branched. So we still have a backbone like so, but in addition to that linear backbone, we have these branches. And they can be of various lengths, depending on how you make it. So this is a branched polymer. It is less crystalline. Depending on how much branching and how long the branches are, maybe it's not crystalline at all, kind of depends. But both of these polymers are made from ethylene as their monomer, right? So just ethylene. And so all of the polyethylenes in the world, so HDPE, LDPE, there's lots of other variations that we don't need to go into. This is the world's #1 polymer, as my PhD advisor liked to say. Polyethylene, world's #1 polymer by a huge margin, and it's not even close. Polyethylene in general has just been used a lot for a lot of different things because it's incredibly useful, and you can make such different materials from it. There are some problems with that, which we'll get into in a bit, but it is incredibly useful. Ethylene is a very cheap monomer, and so you can do a lot of things with it. Okay, so that's isomers, right? So you can have isomers in polymers. The next one I want to talk about is another very common polymer. So this is the floss holder. So I said that the floss inside of the floss holder is a polymer. Well, the holder itself is also a polymer. And this one is particularly interesting because it has a hinge, right? So you've probably seen plastic hinges on things, right? This is one example, like Tic Tac type containers also have this. Anything that you have that has a plastic hinge is probably this type of material, which is polypropylene. Okay, so if ethylene, right, is the 2-carbon alkene, propylene is the 3-carbon alkene. So it looks like this. Propylene, we've got 1, 2, 3 carbons. So when we polymerize it, it is also a vinyl polymer. it looks like this, right? We have that methyl group right there. Okay. So the cool thing about this actually is that we have generated a stereocenter right here because there's also a hydrogen there, right? So here, this is a stereogenic center. And stereochemistry matters a lot. So again, right, we've talked about stereochemistry in this class. Stereochemistry can matter. It definitely matters in this case. And so in polymers, it's less important whether it's R or S, right? Like the absolute configuration. It matters more what is the relative configuration of all of the stereocenters in the polymer. And so in this case, we're talking about isotactic polypropylene. Okay, so iso means same. Tactic is like relative stereochemistry. And so the repeat unit actually is drawn like this. Okay, so we have that wedge out, so it means it's coming towards us. And because it's in the repeat unit, it means that that is also repeated. So if I draw it with all my different colors showing each repeat unit. Oops. Here we go. Draw one more just for good measure. Okay, so that continues on in both directions, but that just shows you a lot of repeat units in a row. And all of these methyl groups, so all of our methyl groups are on the same side. Excuse me. So that's why it's called isotactic, because they're all on the same side. I could have drawn them all dashed back. It doesn't matter. That would still be isotactic polypropylene because it's only the relative configuration and not the absolute configuration that matters. So again, you can tell that this floss holder is opaque, right? So that's telling us that this is a crystalline polymer. Isotactic polypropylene is a very crystalline polymer. And so that makes sense. So most plastic hinges are polypropylene. This stereochemistry gives it that additional kind of toughness that allows it to bend without breaking over and over and over again. And so almost always, if you have a plastic hinge, it's going to be isotactic polypropylene. If you have atactic, which means no stereochemistry, so it's just a random assortment of stereochemistry, that is like a wax. So it is not like a tough plastic. It's not a good hinge. It's like squishy wax. And so stereochemistry matters a ton because we have so many stereocenters in every single molecule. So it really matters. Questions on any of those? Lots of things. So there's lots of things that we use on a day-to-day life that uses plastics. And it actually, like they've been used in lots of good ways, right? So I think we hear a lot about the bad things, which we will get to in a second. But polymers are actually really, really useful because like when they're used for packaging, for example, right, they decrease the weight. And so when shipping packages, you have to spend less energy shipping those packages because they weigh less. So that is important. Or like they also increase the shelf life of food. So you can reduce food waste by using plastic packaging, right? And so like there are lots of benefits, and this is the reason why polymers are used so much. However, there is also an end of life problem that you've probably heard about because it's a little bit more of a modern topic, I would say. And so sustainable polymers has now become a very big thing. And I wanted to put this up here to show that the Center for Sustainable Polymers is something that was started here at the University of Minnesota in the chemistry department. And so this department has been some of the leaders in the entire country of developing sustainable polymers. It has grown, far outgrown the University of Minnesota, but a lot of that started here, and a lot of like the vision of what could be with sustainable polymers started here at Minnesota. And so this center is not really in this same form anymore, but I like this framework because it allows us to think about what does a sustainable polymer mean? And it doesn't just mean one thing. This is a very complex problem that is going to take a lot of different research solutions, right? But we like to use this framework to think about what could a sustainable polymer mean. And so we want to be thinking about, where do our polymer feedstocks come from? So where do those monomers come from, right? So a lot of that ethylene and propylene and those types of things come from like oil, right? Crude oil that we pull from the ground. That's not a sustainable resource, right? And so we would like to start using things that are more bio-based, for example, or a waste product of another industry that's just right now being thrown away. Can we use that and make something useful out of it, right? So that would be a waste feedstock or a recycled feedstock, right? So something that has had a previous life, that's another product we can recycle and then make a polymer out of it. The process is, how do we make those polymers, right? Can we make a polymer in a less toxic way, or that has less waste or less byproducts? So using the principles of green chemistry to try and make these polymers in a more efficient, energy efficient and waste efficient way. And then also, like, what do you do at the end of life? So I think this is the one that gets the most media attention nowadays, I would say. It's like, what do we do with all of the single-use plastics that we have? And it's like, can we match the polymer to the application a little bit better, right? Because if we want to put a polymer pipe in the ground, we want that to last for hundreds of years. But if we're going to use a polymer as a packaging that you use for like 2 days and then it's gone, we don't want that to last 100 years, right? So how do we like better differentiate what is this going to be used for, and can we design a material to better match that application? And so thinking about, okay, at the end of its life, can we recycle it either mechanically, which is what's done now, or chemically? So chemically means that we go back to small molecules. So we can go from the polymer back to the monomer, for example, and then we can recycle those materials. Or is it biodegradable, right? If it ends up in the ocean, will it break down such that we don't need to worry about where it's going to go? Or is it reprocessable? So having a material that you don't, like a tire, for example. Tires are just thrown away because we can't reprocess them. We can't do anything with them. But can we make a material that you can reprocess, that you are able to then make a second life out of it? And then finally, intended use, right? Sustainable polymers, there's a lot of research being done. A lot of it is not economically viable. So eventually you do need to be thinking about that and making sure that it's safe in use. So you've probably seen some water bottles that say BPA free. So BPA is bisphenol A. That is an endocrine disruptor. So it does bad things in your body. And so if you have BPA in a water bottle and then you drink the water with BPA in it, that's very bad. But having BPA in a CD that you never eat, it's fine, right? So it's like really thinking about like, where are you using it and when is it appropriate and when is it not? And so so that's kind of how we think about sustainable polymers. It's no polymer checks all the boxes, right? It's not possible to check all the boxes, but the benefits that we get from polymers are like useful enough that this is like a problem that's worth solving. And so there's lots of people working on a lot of different elements of this, my group included, because I think it's really interesting and I think we're going to have to do it. But there's not just one solution, right? It's not just as simple as like, oh, let's just do this and that will solve the problem. It's way too complicated for that. And so it requires a lot of different solutions and a lot of problem solving. But I wanted to acknowledge that because, yeah, polymers are not bad, but like we need to be thinking more holistically about like where they go at the end. So that is all that I have for you today. So thank you all for a great semester. Best of luck with finals and everything coming up, and wish you all the best in the future.